Heat transfers. Consider two containers, each filled with 100 milliliters of water. The temperature is 50 degrees Celsius in the first container and 100 degrees Celsius in the second container. If I mix the water in my two containers together, what will be the final temperature of the water? It's important to remember that heat is always transferred from a hot object to a cold object, so the hot water will cool down and the cold water will be heated up. The mixture will reach an equilibrium at which all the components will become the same temperature. Since each container initially contains the same volume of the same substance, which in this case is water, the heat capacity of each sample is the same. With this information, we know that the 100-degree sample will lose its heat at the same rate that the 50-degree sample will gain it. The final temperature of the mixture will be halfway between the two initial temperatures, so 75 degrees Celsius. If we mix 10 milliliters of water at 100 degrees Celsius with 40 milliliters of water at 0 degrees Celsius, what will be the final temperature? The 40 milliliter container is 4 times more massive than the 10 milliliter container. Therefore, its heat capacity is 4 times greater. That means that it will be 4 times harder to increase its temperature than it will be to decrease the temperature of the 100-degree water in the 10 milliliter container. We get a ratio of 4 to 1. To simplify our calculation, we want a ratio on a scale of 100 degrees Celsius, so we multiply by 20, and we end up getting a ratio of 80 to 20 instead. This ratio represents the heat capacities of each object, and what we want are the temperature variations, which are the inverses of the heat capacities. The bigger the heat capacity, the harder it is to change the temperature. In other words, the hot water will lose 80 degrees for every 20 degrees gained by the cold water. The final temperature of the water will therefore be 20 degrees Celsius. Now let's consider two different substances. We place 50 grams of metal in 50 grams of water. The initial temperature of the metal is 100 degrees, and the initial temperature of the water is 0. If the specific heat of water is 1.5 times greater than that of the metal in question, what will be the final temperature of the water and of the metal? Again, the heat will be transferred from the hot substance to the cold substance until the two attain an identical final temperature. Since both substances have the same mass, there is no influence on their heat capacities. However, we know that the specific heat of water is 1.5 times greater than that of the metal. We get a heat capacity ratio of 1.5 to 1, meaning that it is 1.5 times harder to modify the temperature of the water than it is for the metal. In other words, the energy that would change the temperature of the metal 1.5 degrees would only change the temperature of the water by 1 degree. To simplify the calculations, again, we want a ratio on a scale of 100 degrees Celsius. By multiplying by 40, we get the ratio 60 to 40. The metal will therefore lose 60 degrees for every 40 degrees gained by the cold water. The mixture's final temperature will be 40 degrees Celsius. Since we have 4.5 times more water than metal, our heat capacity ratio is 4.5 to 1. But we also need to remember that the specific heat of water is 2 times bigger, so we have to multiply the heat capacity of water by 2, getting a ratio of 9 to 1, or 90 to 10. The final temperature of the water is 10 degrees Celsius. We start with a heat capacity ratio of 2 to 1 for water to metal. The specific heat of water is double that of the metal, so we double the heat capacity to get a ratio of 4 to 1, or 80 to 20. The final temperature of the metal is 20 degrees Celsius.